our effort on integrating renewable energy into the electric grid and the role of battery energy storage. So that's the topic that I'm going to present today. Like Rudy said, I am affiliated with the University of North Carolina at Charlotte, and also as in a service role affiliated with IEEE Industry Application Society, IEEE Power and Energy Society. My research background is on power system automation and management, started off with that, and then looking at the ways to integrate renewable energies into the power grid. Last 7 or 8 years, I have been also focusing on how we can utilize battery energy storage as a grid support function, where battery can be used as a controllable asset, and how can we leverage that and use battery along with renewable energy without affecting the grid in the form of instability or quality related aspects, and how we can increase the penetration of renewables. So that's been my focus of research for quite some time. And I have been specifically looking at modeling of the grid with renewables, control of the power grid with renewables, stability and quality related aspects of power grid with renewables, real-time management and integration of the control system as a whole in a central and decentralized manner to connect it with the grid management systems, such as a distribution management system for the power distribution system and energy management system for the power transmission system. So at the PCEL, which we call it Power and Energy Intelligence System Laboratory at UNC Charlotte, we have projects that spans from fundamental research side, supported by agencies like National Science Foundation, industry-based research efforts supported by the utility, local utility, which is Duke Energy, and the Department of Energy applied grants, and also looking for future collaborative initiatives in the area of restoration management, data-driven controls and protection, grid edge, automations, and support of critical infrastructure. So just a brief history of mentoring and deliverables from the PCEL lab. We have power system related research publications, which has been published in journals and conferences, around 200 publications, patents, which is one of the chief area or main area that we have patented was battery energy storage applications with the utility with the Duke Energy, and have had the opportunity to mentor several graduate students who are in the industry working at different levels, including directors at Duke Energy and other industries. And as mentioned earlier, I was able to support these initiatives through grants and contracts of worth around $10 million. So the talk is try to divide into 4 different areas. First, we're going to talk briefly about the global emerging agendas initiated by low carbon goals, and the how the decision support system in the electric utility changes based on these requirements or the mandates which has been set forth for reaching low carbon or net carbon initiatives. So just give a brief overview of that and the role of renewable energy there and the challenges associated with that. And then I will move on to talking about the challenges and opportunities related to battery energy storage system, and specifically focus on electric power distribution system with distributed renewable energy resources, and how the battery energy storage can support functions on electric power distribution system. And I will talk a little bit about the challenges there as opposed to the power transmission system, and the value proposition that we can leverage on the power distribution system. And then later, I will also touch base briefly on microgrids, so-called power grid, electric power grid that can support local loads, and integration of renewables and the battery energy storage system in that segment, and how we can manage the higher penetration of renewables and support functions of renewables on that segment, which is on the microgrid segment. And then we'll summarize the talk. It'll also show you some integration pictures that we have worked with Duke Energy to field integration pictures and the coordination aspects related to it. So I just want to start with a kind of a little bit busy slide, but we'll give you the dynamics and the the key changes that has happened.
Sukumar, are you advancing the slides? We only see the first slide.
Okay, I think there's something wrong with the. Let me stop sharing. I'm not sure. When the recording started, I saw
yeah, you had it in the beginning. Okay, there you go. This is good.
Can you see? Okay.
Yes.
So I hope you might not have missed much. So I was just talking about the research projects in the lab. So different type of research projects. Starting from the fundamental research, the applied research, associated with Duke Energy and Department of Energy and the future research initiatives, and the dissemination deliverables from the lab, including the publications patents and the mentoring activity, wherein students graduated from the lab who are working in the industry. And then talking about the overall, architecture of this presentation. I think you might not have seen these slides, right, Rudy?
Yes, that's right. But we heard you. Thank you. Okay,
sure. So so we divide into 4 parts: the overview, the battery energy storage system challenges and opportunities, specifically focus on electric power distribution system with battery, and then the microgrid. So I'll just present the dynamics of the power utility and the changing dynamics, or changing paradigm, or paradigm shift, which you may call it, in the utility space. So as you can see, there are we can divide them into several parts. The first one is what we call it asset management, where we need to look into asset and how do you utilize these assets with the changing landscape of renewable energy integrating to the power grid. Now, when you look at that renewable energy integration to the power grid, mainly because of the mandate, where we want to reach into the carbon zero initiative, you can see that there are renewables integrated in the power transmission network and also on the power distribution network. The power distribution network specifically will have distributed renewable energy resources coming from starting at the rooftop level on a residential photovoltaics rooftop level, and then have the grid level photovoltaics integrated to the power distribution system. So that distribution system, or the new distribution system as we may call it, is now more active as opposed to the older one. So that's one big change which is happening. And also on the power transmission system, we have renewables integrated. So the first part is asset management related activity. The second part is how do we actively manage the distribution system, which itself is active, which means that the resources on the power distribution system is actively generating power and supporting the loads on the power distribution system. So when we see that, we need to have a management framework that is intelligent in nature, including resilience aspect, where we have a distribution system going down because of maybe natural disaster or maybe because of a man-made disaster, and how do we make sure that the system itself is resilient towards any of these changes or abnormalities. And if such a change happens, how do you restore the system back to normalcy? So this has been an important aspect in the power distribution system. And compounding to that, we would also look into how you can support the critical infrastructure when we have an extremal impact. Infrastructure such as, which are very important, needs to have been there for the, sustaining the life, for example, or human, support systems. So this is actually a very important aspect which has been, changing. And then coupling to that, how we can leverage the value out of these, systems. What is the value proposition? And how can we develop a market mechanism associated with that? We only have, in the United States specifically, we only have capacity market where we have the active power, management done through a market mechanism. A reactive power market is, up and coming. It is not been fully fleshed out. And many of those functions, which we see on the active power region or active power management region, is also coupling or effectively related to the reactive power. So how do we, disengage that and say there are two, related market mechanisms associated with that? That's another challenge. And last, importantly, how we take care of the devices at the last point on the grid, we call it edge device. Last point on the grid, devices are the mostly related to utilization of the energies, for homes or commercial buildings and so forth. How do we manage those devices to control or to actively have renewable energy included in that area or last point or last mile, along with the management of those grid edge device. So as you can see that there is quite a bit of involvement with respect to the management functions, the controlling functions of each devices, management of assets, inclusion of renewable energy, and at the same time moving towards carbon neutrality. Compounding to this, we'll also see we have something called, we call it e-mobility, where we are looking at not just electric grid, but also the transportation sector, moving towards on electrification towards that. So with this, just to give you a dynamics with respect to how the electric grid is evolving, as you probably may know, many of you, but just to give a highlight of this, related activities around that. And then we have this effort going towards integrating renewables, just to move towards low carbon network and the so-called carbon neutrality. The renewable energy integration efforts, which is going on in different parts of the world, you may see that increased proportion of the renewable energy with respect to other energy resources needs to be pushed forward, meaning needs to be increased with respect to the percentage. So how we will have a transition of this network for example, 100% renewable integrated power grid, and if issues related to that. Some of the challenges, as you may already know, is the so-called low inertia systems or no inertia systems. If you have renewables in the power grid, can you have different resources in the mix to have that support mechanism of inertia related issues, such as, for example, nuclear? Can you consider that as a renewable or as a low carbon resource? Or can we go 100% fully renewable? And what are the challenges associated with that with respect to, for example, low carbon or low inertia system? So this is one aspect. The other aspect is the energy efficiency aspect, where you will see how we can improve the energy efficiency with including renewables into the mix. Now, efficiency aspect, it has got multiple effect. One of them will be the distributed nature of those renewables. How can we increase overall efficiency, reduce the losses in the network? How can you make sure that local distributed energy resources are supplied properly? So with this, and on top of that, the effect on the related, because of the climate change effect, such as natural events, now we have pandemic related effects. So how do you move towards carbon neutrality or manage the electric grid? Just to summarize in here, you can see that the renewable energy non-dispatchability or intermittency and variability is one of the technical issues. The other issue is overcapacity in terms of backup protection or backup support systems. Third issue is related to new voltage and frequency needs or changes, and how we can utilize, for example, controllable assets such as battery energy storage to support this. So that's the main premise in here. And on top of that, if you have a system that is affected by natural or man-made disaster, including the solar storms or pandemic-related effects and the issues related to that. So, for example, in here we can see that load change for a system when you are having a pandemic is different from the load change or load shape when everything is up and on board. So the load forecasting or the load management techniques based on how the load shape is effectively understood previously has to be restudied or needs to be studied again. So you can see in here the shape related to the load remains the same, but you can see that the total magnitude or the shift on that is different. So this is now becoming more like a net load, we call it. If you have with renewables, the load shape, what we see with renewables are not the total normal load, and we call that as a net load. So this is similar to that. So, the related aspects on natural disaster and that pandemic is a critical part. Now, if you have to manage the power grid in terms of normal operation and in terms of abnormal conditions, we need to have to see how you can operate the grid when the grid goes down and how we can bring it back, to restore it back in full restoration phase. So there are mainly 4 aspects that we should consider if you transition from a grid, which is normally operating, going to abnormal operation and coming back to the normal operation. That includes the ability of the devices to make sure that the grid outage is reduced, which is in terms of speed, in terms of selectivity, in terms of sensitivity, and obviously last but not the least, in terms of sanity, to make sure that the outage time which you have on the power grid or electric grid is as low as possible. So this is a classical representation of what we call that as a resilience curve, where you can see that the normal operating condition of the grid, and then we have the degraded state of the grid, which is basically happens because of the abnormal conditions on the grid. And how do you restore the grid back to, so this is your complete, full operation stage. How do you restore the grid back, and based on your response recovery? And then you have a state which we call it as a post-restoration state, which is robustness resistant state. and then you bring this grid back to the full restoration phase. Now, in all these phases, how distributed energy resources will react and how battery energy storage systems can be used to support the grid in normal operating conditions, abnormal operating conditions, restoration phase, and the full back to normal operating conditions is the key important next generation research to me, at least in my mind, for the people will be working on. We just started as on that research, tip of the iceberg. We are starting on the normal operating condition now, and we will have to follow this whole path and how we can, with renewables and battery energy storage, how we can improve the performance of the electric grid on all these operating phases. So having said that, I will show you a brief picture on the current decision support system or evolving decision support system in the electric grid, and the highlighting the areas of the battery energy storage part. So if you look at the power grid as a whole, you will see that the electric grid on the top layer is basically managed by the so-called EMS or energy management system. This energy management system previously in yesteryears used to have a SCADA-enabled large-scale centralized power system management center or operating center, we may call it. Recently, with the advent of integration of renewable energy and the battery energy storage, all in a centralized plant or partially distributed plant. So this EMS functionality has been improved with mostly using measurements as opposed to the SCADA-enabled EMS. So there is one good group of research which is happening there on measurement-based energy management system, where you have on the transmission system, how we can utilize the sensors, so-called phasor measurement units, and the use of that to improve the energy management system capability on the power transmission system. Now, when you look at the power distribution system, it's very interesting. Initially, used to have a management system on the power distribution level called DMS, or distribution system management or distribution management system. With the distribution system becoming more active and have multiple stakeholders, this distribution system management systems have been evolving to several different parts which is connected to the DMS or distribution management system. Some of those terms I'm going to highlight in here. One is to get the information from the regions or the customer through meters, and it comes under the umbrella of AMI or advanced meter infrastructure. Then we have the systems which is evolving to manage homes or smart homes called home energy management system. And then we have commercial entity management system, which is including the factory energy management system. That's one of the aspects. And then we have building energy management system, which is maybe mostly on the commercial side, and electric vehicles management system. This is on the lower end, which is basically what we can call it as a grid edge kind of area. Then we have this community energy management system, which is being used to have a support functionality in a community or in an area connected to the functionality of the DMS extended, what we call it as ADMS or advanced DMS, which includes distributed energy resource management system or DERMS, and related other functionalities of the DMS called outage management system and all that. So as you can see here, there are multiple aggregated functions which is happening is related to different stakeholders or related to the utility itself integrated back into DMS. So management at this level, which is on the distribution level, is becoming very complex or more complex, and getting the value proposition out of that and the effectiveness of the battery energy storage to support on the DMS or distribution level is very, very critical. So having said that, there are two main aspects which I think personally that is important in the future context. One, how do you manage or control different assets in the power distribution system? What are the methods of management and control of these different assets?
And Shankar. or for others.
The second aspect is related to how are we going to understand which functions are critical at what stage or what point. So two things. Number one, finding out the functions which is important for the battery energy storage and also related to the distribution management system, number one. Number two, how do you manage or control? So having said that, now I will start talking briefly about the battery energy storage system challenges and opportunities. In this time, I'm going to be very brief, and I'm going to talk about the main functions that we have utilized or we have been proposing and implemented in the power utility. This is specific to your interest, so I'm just going to talk only about that. But there are some additional functions of these battery energy storage system, management infrastructure that we are building in because of the need and the changes which happens on the utilities. I'm going to talk about that too. So let's talk briefly the functionalities for what battery can do, to support electric grid in presence of renewables. So the first part of these battery functions are to do with how can we reduce or mitigate the negative effects of the renewable energy integration, which could be centralized or could be distributed. Now, there are mainly two negative effects of renewable energy integration to the power grid. One is related to the change in the output coming from the renewable energy. We call them as non-dispatchable energy resources, which means you cannot get the power you want at any given point of time. It is dependent upon where the sun is and how much of the cloud coverage is, for example, for the photovoltaics, or where the wind is blowing. So we call them as intermittent resources. Intermittency is mainly related to photovoltaics. The wind farms, we are normally considered as variable resources, not very intermittent, which means that the output power is varying, but it is not very highly intermittent. So there are two different aspects there, intermittency versus variability. But in general, you can call that one of the challenge is intermittent related resource integration to the utility if you have a renewable energy resource. That's number one. Number two is that the power that is coming out from the renewable energy resource may not be the power as you want all the time, even if you have the full capacity, because the fuel, which we call it sunlight or the wind, is not going to be the same throughout. So there are two aspects. One is to have additional capacity to offset these changes, number one. Number two, to firm or to make sure the output for the renewables are constant. So this is related to the renewable energy integration. The second piece where the power grid can get benefit out of the battery energy storage is the support functions to the grid. In general, this is called as auxiliary support functions, which means that how, with the help of renewable integration to the grid, or in general, otherwise too, is the grid impacted? Is the stability of the grid being affected? And if the stability of the grid being affected, how can you support the grid so that the grid will not have unstable conditions? Now, stability can be divided into, as you may call it in general, frequency-based stability issues. You can also have related aspects such as spinning results, and you can also have the because of the power transfer from point A to point B and the challenges associated with that. For example, the capacity increase or capacity upgrade of the transmission lines or distribution lines. Can we defer them? Can we move? Can we have some other support, energy support at local, rather than transporting power from point A to point B? So that's the additional aspect related to that. And not only that, can we smooth or can we have a constant power demand from the generating resources rather than having a changing power demand? from the generating resources, which means can we make sure that the power demand, power when it goes high, you shave that power, or when the power goes low, you fill that power with the help of energy resource. So this is basically on the transmission side. On the power distribution side, it's very, very interesting. We don't have, so all these one on the transmission side, by the way, has got a value which you can associate with. For example, frequency regulation, as you can see, or T&D upgrade deferral, spinning reserve, peaking resource management, or flexibility associated that. All of them you can relate to capacity or related to active power management. So you can have a value which can associate with that. On the distribution side, as opposed to on the transmission side, many challenges are related to the changes in voltage profile or changes in the current with respect to the power flowing through these lines. Now, when it comes to that, you can have more improved voltage profile or better voltage profile associated with that, or you can have the, making sure that power is given to specific areas to improve the total resilience, and the asset management in the distribution system for power flowing back to the transmission system, and then challenges associated with that on the asset, for example, transformers on the feeder head or the substation. So with these, you can see many of these challenges are related to what we call voltage profile or the reactive power management. So how do we value that? How do you actually give monetary value for these kind of support functions is the main, one of the main challenge. So, but in distribution system, you have the support functionality associated with voltage improvement, capacity firming of the renewables, for example, photovoltaics, changing the power from one point to the moving to the other point, you call it energy shifting or energy or power shifting or energy shifting from one location to another, and associated functions related to that, so-called energy arbitrage and things like that. So energy and power related changes you can provide a value to it, but the voltage related changes, it's very difficult to provide a value to it because we don't have any reactive power market associated with that. So the challenges are operational value in all the times in all the operations that we have for the battery energy storage. Where do you locate the battery energy storage and size of the battery energy storage associated with that? How do you make sure that interconnection to the battery energy storage to the utility is done properly? What are the resources? Who are the stakeholders associated with that? And the last, but very important, is management and control and integration of that with respect to existing management system, so-called DMS. So these are the main 3 or 4 challenges which we currently face with respect to the integration of battery energy storage to do the grid support functions. So with this, I'm going to talk briefly about what we have done on the battery energy storage system integration in the power distribution system with photovoltaics. And I'm going to talk about one approach that we implemented, designed, developed, and implemented in the field called stacked energy storage approach, where we have functionalities of the energy storage stacked on top of each other, or can stack on top of each other, and then can provide a value proposition associated with that. So this picture, I just put all of them together in one slide. This picture showcased the value propositions or the functionalities of the battery energy storage in the power distribution system. What we have implemented in the field is what you see in here. What we have not implemented this field and advanced talk about a little bit later in the presentation. So in the power distribution system, we were looking at mainly 3 functions for the battery energy storage. One was renewables firming or renewable capacity firming. I'm going to talk briefly about that, which is obviously related to making sure that intermittent nature of renewables are not seen at the feeder level or the point where the renewable energy is connected to the grid, point of common coupling, people may call it, but point of common coupling is not always the point where you connect the renewables to the grid in the distribution end, as opposed to the transmission system. But in general, you can call it as, point of interconnection is how it is called, but point of common coupling is another word which you can use it. So how do you make sure that the power at that level is firmed or smooth? That's number one. Number two, how do you have an energy time shift algorithm that you can utilize to use the battery energy storage to make sure that power where the photovoltaics are not available or low can be supported. We're not talking about the nighttime, but other than that, when the power from the sunlight is low, how you can support support that power requirement utilizing battery. And the last one is voltage support. The voltage support has basically two different type of support there. One is making sure that voltage at specific points in the utility or on the power distribution system is maintained, or make sure that the quality of that voltage profile is good, voltage at one point. Second one is entire voltage profile throughout the feeder, coordinating with multiple legacy controllers, such as voltage regulators, have been maintained or controlled properly. So these are the main three functions that we have implemented in the field. Now, to do this, one of the requirement in the field implementation was to not use a lot of forecasting techniques, but utilize measurements. So the data that is collected from the medium voltage feeder includes voltages, the point of measurement, load curves, which is historic, voltage regulator meter points, active and reactive power coming from there. Energy storage system data, including reactive power, state of charge, and the voltage level. And the how we use this is by looking at the feeder load or feeder PV output projection and developing the power, which is as a set point power or a reference power to the battery, to make sure that the power from the battery is generated to offset that intermittency. So I'm going to talk about that algorithm specifically a little bit later. And the only two other parameters that we use for this optimization or this control architecture is the TAPS operation of the voltage regulator and the cloud state, which is utilizing a meter called WeatherHawk, which is basically looking at the weather profile. So these are the sensor that is we call it sensor or measurement that is utilized for this approach. And the effect on the feeder operation is you can provide a value associated with monetary value associated with that, and then you can have a value-based optimization. So now I'm going to briefly talk about the value chart with respect to the overarching benefit. So the benefit is obviously improvement in what we call it reliability. Reliability, you can think that as a superset of the quality and stability aspects associated with this. So quality and stability will finally come to the outage time or come to the mal-operation of the devices, and you can bring that in the umbrella of the improvement in reliability. So prioritizing and implementing value-based algorithm is based on the value which is coming to the grid in the form of reliability, and then the economic benefit associated with that. So you have the value-based energy storage applications, you have the knowledge that is been coming from the system, and then we get that operational value associated with this. And that operational value in the form of economic benefit, if you can quantify, can be brought as in the closed loop as a function of the grid variables such as voltages and the load power. So that's basically your overall value proposition chart. So, as we are looking at a for-profit, framework, we also need to have some kind of a business model associated with this. So we divide the business model proposition in the form of knowledge gathering, how we are getting the information from the field, then the applications, which applications connect to that knowledge gathering. So for example, if you wanted to calculate the power reference to, from PV and the battery power, and look at how the battery and active and reactive power is being calculated, you use the knowledge and then you identify which storage applications can give you better value proposition. And depending upon those identification, which is integration of the measurements as well as the grid functionality, you choose what type of functionality for the battery that you want to perform. So that's basically the overall idea in there. So once you choose that, then you can prioritize which application you should use at what time, or combination of applications which you may want to use at a specific time. So that's the advantage of this, what we call it as the stacked approach, which means all the functionalities are available for you. Depending upon the time of the day or depending upon how you want to utilize, you can mix and match or have a combined functionality applied to your controller, through your controller applied to the battery energy storage system. So that's the overall architecture in here. Briefly about the I just mentioned this before, but just to give you an idea, if you are not very familiar with this, the capacity, active power coming out from the battery is basically the energy and power that you can utilize. It can be used for PV smoothing, or for example, energy arbitrage. Everything is active power related. The reactive power coming out from the battery is through your DC to AC converters, which is connected. So this reactive power capacity is tightly associated with the converter or the inverter, we call it, which is connected along with the battery. Now, if it is a grid asset, you can have a battery, for example, which is 250 kW and 750 kWh battery. You can have a 1 MVA capacity for an inverter, where you have additional cushion or a room to have the reactive power, extra reactive power coming out from the inverter. Now, as you may know, the reactive power support from the inverter is different than the conventional way of supporting reactive power in the utility through capacitors support or capacitor related support or voltage management directly from the regulator, because the battery the reactive power coming out from the inverter is through the angular shift between the current and voltage, which happens inside the inverter. So it's a kind of a free commodity which you can get from the inverter itself. However, you wanted to make sure that that capacity is sized properly, or the inverter is sized properly, so that the total MVA rating of that inverter has enough reactive power requirement which is needed at that specific location. So I don't know whether you are familiar with that. So I just wanted to mention that to you. So the reactive power which is coming from the battery energy storage system obviously can be utilized for two purposes. One is voltage support, another is volt-var coordination. So volt-var coordination and voltage supports are actually, when you look at it, it may sound same or similar, but they're two different functionalities. So the volt-var coordination with respect to the legacy devices, for example, voltage regulator, and support related to the volt-var coordination or volt-var, basically VAR support. Then the voltage support is based looking at what is there on the voltage profile. So two different functions that you can have from the reactive power. Now, with those two functions has got few other attributes associated with that, depending upon the size of the battery energy storage, distributed nature of the battery energy storage, and so forth. I'm not going into that detail, but I just wanted to mention there are two different group or bucket. As we discussed before, this may have a monetary value direct, but the reactive power do not have a monetary value as such by itself. That's the biggest challenge. So can you relate that to a monetary value by connecting to the watt or the real power of the distribution system or the device? That's the things that we can do. So there is something called volt var watt support, so you can actually do voltage var and watt connected together, and there is a tight correlation in the distribution system with respect to, because of the what we call is the X by R ratio of the distribution system being low, we call it, so that is another aspect that we can utilize. But in any case, there are two different functionality. For both of them, you will have the changes with respect to renewables and the load profile going into an optimization routine. And then we'll look into the percentage as a value proposition, look into the percentage PV smoothing and energy arbitrage at voltage support capability. So having said that, I'm now jumping into use cases and some of the finer details of this algorithm. But before I do that, I just wanted to show you a map in here, which talks about the conventional power grid decision support system. On the left-hand side, this circle is for the transmission system, which is, like I said, improved from the SCADA, moving more towards the sensor-based or measurement-based transmission system management. This is thanks to the phasor measurement unit deployment and the capability associated with that. We can have measurement-based control on the transmission side. And because of that, we can have also wider area management, control of the transmission system. On the distribution system, there is a DMS coming under the power delivery segment. DMS has got functionalities, including operational management and optimization, distribution system automation, hierarchical centralized distributed aggregator. Because of the new, or through the new mandate from FERC, which is 2222, we also have the aggregated based control that can go to stakeholders beyond the utility itself. So that's another thread that is connected in here. Distributed resource management and distributed energy resource management. These are two different terms that we used. And obviously at the last point, the AMI. So if we were to control the battery energy storage and functionality, how we integrate this to the other functionality is also an important thing that you should keep in mind. So that's the reason I wanted to bring this slide up. So there is a new work that we are doing currently with the help of Department of Energy Solar Technology Office. The architecture is management and control of local assets, and how you make it resilient, utilizing all the distributed energy resources like photovoltaics, and using battery energy storage as a controllable asset. So if you are interested, please, you can go to this website as www.redispv.org. This is more like a consortium. There are a lot of people involved, including national labs and other universities. So this is an advanced function which is not implemented in the field yet. We are currently looking at working with Duke Energy to work on implementing on the field models. But here the goal is to have how to group the distributed energy resources virtually, not like a virtual power plant, but a virtual grouping, call it clusters, and it's dynamically changing clusters and then manage them. So that's the focus of this work. So I just want to talk about the control aspect. So with this, I'm going to talk briefly about what has been implemented in the field, and then summarize the overall effort. So here, the field architecture looks like this, where you can see the historical data log coming from the utility. This can be through the archival, maybe Pi server or any other server archival on the utility level. It's we deployed into on a PV 1 megawatt PV station and have a battery energy storage 250 kW, 750 kWh with the inverter capacity of 1 MVA on radial distribution system. And then using the historical log, looking at 3 functions: renewable energy capacity firming, renewable time shift, and the voltage support. So I'm going to talk in this blocks. You may see the key aspect of this algorithm is based on what we call it a firming reference optimization routine, which you see a block in here. You can see my cursor, right? And the one which I'm moving. Okay, so it's a firming optimization. That is one. And then we have the calculation logics for based on the load prediction, the energy calculation logic, and then utilizing whether we have to have a reactive power requirement or not. This is reactive power requirement calculation is different if we look at voltage profile, where we need a sensitivity-based calculation for the entire feeder, as opposed to 1 point volt hour support. So I will just talk about two different variations on that reactive power, and then have a value priority stack that I said, as I said before, can be used to see whether we need to use one functions or a combined function. So as far as a technical aspect is concerned, I'm just going to talk only about one part, which is called the reference curve generation. This approach is based on how you generate a reference value of the photovoltaic as a reference set point for the battery. So if you look at a photovoltaic, you will see that the photovoltaics outputs are vary with respect to time and with respect to season. So how we do this, calculating the reference, is looking at the past 7 days historical value. Like I said, we are not doing any forecast. We are only doing, precast values, where you look into the previous values of the photovoltaics, finding out the minimum and maximum value. And then based on the minimum and maximum value, we create a reference value within that minimum and maximum. And utilizing the reference value, we call that the change in that reference value is associated with the reference for the power coming from the point of common coupling. So that's the key aspect of this algorithm. And once we have the power coming from the point of common coupling, you can utilize that as a reference point for the battery by subtracting with the PV measurement, which happens at a current time, not again forecast. So if you look at the objective of the function for this optimization routine, this is an optimization algorithm, mainly error minimization based optimization. We are not doing any value based optimization with respect to, for example, the loss minimization or cost of the generation. You can superimpose that optimization level, but here it is just error minimization. So once we have the reference with the set, and we call set as a kind of based on an equinox and based on where the sun is moving, you can create a skewed or close to a sine wave as a reference point. And if you have that, the goal is to minimize that optimization routine with respect to the time. It can be a day or it can be hour, depending upon how you look at it. And then once you have that, you actually create a output, which we call it an M value, and utilize that M value to create the PCC reference. So that's the main idea here. So here are some output reference graphs which you can see. Here you can see from the older historical value, you can create a minimum and maximum change for those historical value, and then develop a PCC reference curve, we may call it. And with the help of this PCC reference curve, you can use that PCC reference curve to provide a set point to your battery energy storage. And so you can see that this is the PV for that specific day, and this is one specific day set point for a one full day information. So this is a set point which is coming out from the PV. Now with that set point, the battery reference is changing. So this is a battery reference. And then the output of the PCC, which is PV and a battery coupled with that at specific point, you'll get the output of the PCC, which is you can see right here. So the whole goal here is to strengthen the capacity, or rather smooth the PV, rather not even strengthening the capacity, smooth the PV with the help of the battery energy storage, which can be further strengthened later if we have this part of the PV, or rather the support from the battery for this part, we can strengthen the output with respect to whatever that output. Now, we need to have some kind of a metrics associated with this to evaluate the quality. So what we do is we look at the total 5-minute PV differential, we call it at KW, and the PCC differential. So you plot the PV differential and PCC differential and look at a kind of a slope And the goal is to see how that slope changes. So if you see that slope, basically is going towards on this side, which means we have a, a smoother profile as opposed to the slope which is on the other side. So that's how you can see in here with respect to the smoothing and without smoothing. Now, how do you convert this into a dollar? There is a mechanism to do that. We have developed a mechanism to do that, to see what is that conversion will be. But that depends on several other factors. So it is changing from the utility to utility, and a different utility. So in general, you can use that as a metric, and you can say that for a improvement with respect to the smoothing index, we call it. So that smoothing index improvement can be attributed towards the change. So we have two methods in here. I'm not going to explain both the methods, but you can see that the 5-second PCC values changes is substantially reduced as opposed to the PV output change in here. And that is exactly what we are looking at to see how related to smoothing, how we can quantify with respect to the value. So essence of time, I'm going to talk a bigger architecture where we have included the PV smoothing or the capacity firming along with the reactive power support. So on the right hand side, you will see the energy storage sizing and energy storage sizing related, network reference generation, the ramp rate calculation. So here, when I talked about the first one, I didn't discuss about the state of charge of the energy storage. How do you control the state of charge? What's the ramp rate associated with that? So I'm just going to showcase an integrated, full-fledged, full-stack algorithm now, and we can discuss offline or have some material sent to you if you are more interested to look at the finer details of it. So in this full-fledged algorithm, you have the photovoltaics capacity firming on the right-hand side, where you can see in here. On the left-hand side, relating the voltage-related problems, relating the legacy controller with the voltage-related problems. So the legacy controllers includes the two type of legacy controllers, regulators and OLTC. Their functionality is a little different. In the utility space, people will know, so the difference related to that. We get a DMS output with this voltage-related regulators and capacitors and obviously OLTCs. With that, you look at the sensitivity of the slow changing load and dynamically fast changing load and the PVs. Generate two reactive power reference, one based on each of those time scale or separation or the sensitivity. From there, generate the QREF at the PCC and calculate the limits for the battery related to the inverter, as I called previously, because it depends on reactive power, it depends upon the inverter. So calculate the limit, include the warning detected from the taps from operation of the regulators. And then from there, looking at the reactive power capability, calculating from the real power, and then setting as a P set and Q set. So one aspect of it is coordinating with the battery energy, with the regulators. So as you can see that with the help of this effective coordination of the reactive power and active power, the number of tap operations on the left-hand side of the regulators are less. We try to capture that as a dollar value, but that's not a big dollar value, as you may know, because the number of tap operation and the tap failure and life cycle associated with that is very not a big value, but it can be a big value if you have renewable energy intermittent. So that is one aspect. The second aspect is obviously the voltage violations and the voltage band. So you can see in here how the voltage is being regulated on the regulator point, so this is not profile management. So regulator point, you can see that the voltage, are balanced much more. So that's one aspect. And then we go with the profile management, where you are going to find the regulator outputs based on the measurement, create a sensitivity matrix for the entire system, and then see whether we can have the profile managed properly. So here, this is an example of the secondary side of the voltage regulator output with the volt-to-hour control and a sensitivity-based volt-hour control. So you can see that the profiles are much more flatter as opposed to this with respect to the sensitivity-based management control. And finally, we included the VVC and VWC and VVWC. So here VVC stands for the reactive power control on the feeder. VWC stands for the active power control on the feeder. And VVWC stands for the active power and the reactive power control on the feeder. Based on that architecture, I just showcased. So this one is not implemented on the field, the VVWC, but we implemented it on the real-life power distribution system, which is also called as IEEE feeder 8500 node. It's a feeder in North Carolina. So we have used 3 battery energy storage, called that feeder as a 3 subsystem, and then showcase the effectiveness of that with 3 PV profiles, which is from realistic PV output, and 3 battery energy storage, 300 kW each. So the sizing and the location, like I said, is another aspect that we should be looking at. Right now we looked at, so one way to look at the location is at the regulator points. Basically, that's the controllable points on the distribution system. Naturally, you can use that as a point with the high penetration of PV. So now you can see that this is an example where you can see the effectiveness. We call this as a local duct. This is more like a duct curve, as you may know. This is done in the EMS or the aggregated duct. This at any PCC or any sub area in the distribution system, you can see that with the help of intermittency improvement as well as this shifting, you can improve this duct curve. So you can see this light dot there is the one that is improving. So you can see they are less intermittent. And also you can see they are moving down, which means it's should be more like a flat line, right? So depending upon the capacity, you can make this as a straight line. Now, is a straight line a good thing for you, or what's the value associated with that? You can calculate with respect to the capacity and then decide whether we should do only intermittency or whether we should do intermittency as well as shifting, and then make this as a straight line. So that's basically the value part in there. And as opposed to that, you will also see the reactive power coming out from the battery energy storage on the left-hand side. The active power, as you can see, this is the active power output. And the voltage profile. So you have 2 benefits, like I said. One is obviously the active power management. Second is a reactive power and voltage profile management. So you can see the voltage on the different points of the regulator, how that has been controlled or smoothened. That's first aspect. And the colors, with the colors, it is probably very visible for you with respect to the voltage profile management. We also looked at in the form of a quantification table. So you can see the number of operations of the tap operations of each of those regulators are one aspect that we utilize to see how good the algorithm perform. For coordination aspect of voltages, so you can see the number of taps getting low is an important part. We went to an extent that to see whether we can do something called asset release, which means that there is no tap operation for the regulator for 1 full year, which means you can take that asset out and then use it for some other purpose, right? So that is something also which we can think of coming up with the value proposition. I mentioned about the trouble in getting value proposition in the distribution system. So that's one. The second one is a VDI, we call it an index of the voltage deviation, how the voltage deviation index is improved. That's for the profile, not for the regulator aspects. And then how you actually have a ramp rate improvement with respect to the substation and the loss, power loss improvement so as a function. So I think we are very close with respect to the time limit, right, Rudy?
Yes. Mm-hmm.
So, well, this architecture can be utilized on the, visible PV output or the utility-owned PV can be utilized on the non-utility owned PV or on the rooftop PV as well, which can be used for grid standalone systems and the grid support system, which is one of the features of the microgrid. So you can actually have aggregators that can be included at the each points of the grid edge, on each phase. So one of the thing about on the last point or last mile is that the asset or the PV and the batteries can come not just in 3-phase, but also can be in single phase. So each phase control and the phase balancing, as well as the voltage profile related to what we call mutual coupling, and then issues associated with that, it's another challenge. So we should have a way to do what we call 3-phase management on the lower end of the distribution system, or rather the edge device. So you can see some of those on each of those phases. You can utilize, integrate that with an aggregator. Local scheduler based on optimal scheduler. Local scheduler is given to because there are 2 ownership now. One is the customer, and the other one is obviously the utility. So local versus optimal scheduling, how you do that, and how you disconnect and reconnect that. So an architecture has been developed and then implemented in the microgrid. Again, not implemented in the field, but implemented utilizing the field information of this with the system. Now we are expanding that into the cluster management, utilizing the Department of Energy funding, where we are using the photovoltaics as single phase and 3-phase, all combinations, behind the meter or in front of the meter. Behind the meter, we are saying that the measurements are available only on the outside the meter, and they are not controllable assets with respect to the batteries, maybe or may not be. So how you use that as a cluster, as a group, without knowing the individual load. So that's another work which we are looking at. So having said that, I hope I gave you enough details about the battery energy storage system challenges and main challenges and opportunities. Given the fact that the value proposition, monetary value proposition in the utility distribution system is not fully proven or fleshed out, how you can utilize the battery energy storage as a stacked energy storage approach, how design the algorithm and implement in the field, and then kind of so-called look into the overall economic value and the extension of that with respect to the distributed storage. So here are a couple of patents and then few publications that is associated with this work. You can see other publications on my website where we list all the publications which is coming related to this area. I'd like to thank acknowledge the support from Duke Energy, National Science Foundation, and other related efforts, PCell, Power and Energy Intelligence System Lab researchers, alumni who are in the field now, working in different places like Hitachi Energy, Duke Energy, and SEL and national labs and other places. And I also like to thank you all for the invitation.
Thank you, Sukumar. That's the most comprehensive treatment I've heard. So as we do in the past, I would like to have the first set of questions come from students. Students, please unmute yourself and ask your question. Or you can put your question in the chat box and Susan and I will go through them. So students, please ask your questions now.
I have a question. This is Carol Obando Durstein. Thank you so much for the presentation. It was quite comprehensive. Although I have to admit, I'm going to have to go back to the YouTube video and watch this and pause it. You covered a lot. Okay. So my question is, because I'm also interested in how to quantify the benefits of a BESS on the distribution system, and specifically for voltage support, like you were definitely talking about. But did I catch it right? Like most of the study that you have done is for almost like behind the meter batteries. So it would be like on the customer side. And I have been interested in a utility scale battery, so upstream of the customer.
Yeah, so most of the study that we have done is on the utility scale battery, not on the customer side.
Oh, okay. So
yes,
then that, okay.
So that's appropriate for your requirements or your thought, I guess.
Okay, and you said the second part is that it was very different for, okay, yeah, thank you for that. So you had said the benefits are from utility to utility. So would I be able to just find more of those details on the links that you mentioned?
Yes, we can chat. Definitely, I can give you my experience and perspective on this with respect to implementing it on Duke Energy. So this is actually a slide. It's a slide that showcases how these controllers are designed in the lab, and the battery in the field is 250 kW. It's a utility scale battery. The battery from Qualcomm, and the SNC is the inverter manufacturer. So I can share some experience and how we did it in the field. What are the value propositions that you should look into, and what are the differences that we think which will happen between utility to utility, if we can take
Excellent.
it offline.
Oh, that would be perfect. Thank you so much.
No problem.
Okay, thank you, Ms. Carol. Questions from students? Unmute yourself, introduce yourself, and ask a question, please.
Hi, I'm Nick here. I have a question about you said you focused on utility scale batteries, but would there be a potential for behind the meter batteries where a customer, a solar owner owns their own battery system and provides smoothing and then gets a financial reward in return? I don't know if any systems like that exist yet, or if that's just something that's going to be in the future more.
Yes, there is a big potential. Your first question. Yes, there is a big potential. But unfortunately, right now, the only incentive that you can get for a rooftop PV kind of a framework is utilizing the so-called net metering, or in some places, at least we have this in North Carolina, we have it, but not many other, maybe some other places too, where your credit is for the energy, not for the grid support functions. So it's two different spots, right? So the smoothing and the capacity firming, all those comes under ancillary service or grid support function. So to get a credit associated with that, we need to have that, rate pay or the policy or a setting up of that credit. That's not there existing. But potentially, yes, that is the value that we can unearth with help of these modeling aspects and studies and showcase that value. And much of those is also because we don't have a lot of renewable energy penetration in the grid as such. We may call it we have, but we don't have, only 13%, 14%, 15%. We are hovering around that. If you look at the aggregated penetration, and once you increase that, you will see that problems, right? So then your related to credit will come, but not there right now. Does that answer your question? Hopefully.
Yeah, that answered it. Thank you.
Questions from students? Unmute yourself and ask a question, please. So Sukumar, while we wait for a question, am I correct in, your capability demonstrates that you don't have to have a battery just for one specific usage, either smoothing or deferral or frequency regulation. You do this dynamically with, depending upon what the value is at that particular instant. Is it in frequency regulation? Is it in voltage smoothing? Signal smoothing or voltage support? Is that correct?
That is correct. That is exactly right. Yes. So the main decision that we took to go with what we call it as stacked approach is understanding the fact that we cannot demarcate or differentiate at a given point of time. You need one function, or at some point of time, you just need only one function. That's very difficult because the coupling effect of the active and reactive power in the distribution system is quite a big, number one. Number two, the value proposition that you get is different or dynamic or it's changing. So you need to look at holistically in this whole process of what we call it as the functional management. So instead of going with that compartmentalized functional approach where you have each of those functions attended separately, we went with a stacked approach where all of them can be done at the same time, or you can mix and match depending upon your priority.
Yes. And did you also demonstrate, Sukumar, that using the stacked approach is beneficial economically? I mean, did you demonstrate that?
Yeah. So this work that we have implemented in the field, having the, few value streams that we may call it, for example, energy time shift, capacity firming, deferral, and on top of that, volt-var, watt management combined together. We show the benefit. So the metrics that we show, when all of them combined, what is the effect of on multiple, value streams? That is what we have showcased in the field.
I'm just curious, is anybody doing anything along these lines? Anybody else?
No, I think it is no, I have not seen anybody who doing this stacked approach. That's one of the key factor for it. I mean, key innovation, which you may call it in this area. I have not seen anybody doing that. So I think it is very valuable, but the it can be adapted into different settings, which needs to be unearthed. So hopefully other stakeholders will catch on to this, and then will improve on that.
Okay, questions from the general audience. Please unmute yourself and ask a question, introduce yourself, or you can put it in the chat box. Questions from the general audience? No questions? Questions from the audience? Any general question?
Yes, I have a question.
Yes, please.
This is how long. I have a question. What you're doing, I'm really simplifying it, but you're smoothing out the response from the solar. We get during the day you have energy, and at nighttime you don't, and you're kind of smoothing out when the solar is active, and making it more amenable to the power system. But what are batteries going to be able to help when there is no sun? I mean, can you store energy enough when there's excess energy, and then put it out when at nighttime, for instance, to smooth it out, to provide power throughout the day?
Yeah, excellent question. Yes, we have sort of two parts in that question, I guess. First is, if I understand correctly, the first part is, do we have enough, make sure that we have enough juice in the battery to do this smoothing effectively day in and day out, every day? That's one part, I guess, right? That's one.
Yes.
So we implemented this in the field for almost two separate seasons, one on the shoulder month, which we call it, where the power which is coming out from the photovoltaics and seasonal changes related to that, it's a little bit more varying, and then one on the winter time. So in both cases, in multiple days, to make sure that the battery state of charge is basically required. So the state of charge, I have not actually went into the state of charge discussions in this presentation. So the state of charge reference point, most likely we say that 50% is a great, because you can have up shift and down shift smoothing on positive and negative side, but that's not necessarily true all the time. Sometimes you may need a 40%. So I'm talking only about the smoothing, not the nighttime. I'll come to the second part of it.
Yes.
So the higher and lower values of the percentage threshold or the reference for the state of charge has to be shifted maybe 60% to maybe 40%. Also, depending upon the type of the battery, the deep battery can go from 10% to 90%. Some of them will only go from 20 to 80%. So you have to consider that band, which is what we call as a minimum to maximum band. So we used a lithium iron phosphate battery, which can go, it's a deep from going to go from 10%, 90%. So that's possible. So we tested it, long story short, with in the optimization, considering the battery state of charge. And we have tested it throughout, and there is no loss of energy in the battery as such with respect to smoothing. Now, the second part on the nighttime support, that is related to the sizing. So you cannot actually, once the sunlight is off, then obviously it's completely related to the sizing. So what we have done is we wanted to bring the battery state of charge to 50% or 60% state of charge before the day is out, so that next day morning we can start from that reference set point. So that reference set point is, you have to look at from previous historical day, whether it's 45 or 55, like I said before, to begin the day. That is, I think, is a little bit tricky part, but we wanted to make sure that it's being charged at that rate when the next day begins. So we did that, and it works.
Okay. Now, but what do you do when there is no sun? Have you thought about including, obviously you probably have, but wind energy also in your grid? How would that work with batteries too?
Yeah, so the battery support functions for there is no sunlight is a little tricky, because I don't think we are there, honestly speaking, at that dollar point with respect to the battery technology advances, where battery can be utilized as an asset that can actually completely firm what we call it, or straighten that line. We are still hovering around, I think last when I heard $180 or $200 or something like that with respect to the battery pricing, I'm talking about. So I think we're not there yet. However, if we mix that with respect to other resources, so for example, peaking resources, there is a value proposition that we found where with the peaking resource and the battery, for example, pumped hydro or hydro for that matter, in a specific region, not for it working for every region, we can actually offset and have a value proposition associated there. So having said that, we still need to get probably 1 or 2 notch below with respect to the dollar for the battery technology, but we are getting there.
Okay.
If that answers your question, I think that's probably your leading.
Well, just one more, just to clarify. How about, have you considered wind farms in your analysis at all?
Yeah, so we did a lab testing with the wind farm along with the battery. Considering that, as you may already know, maybe that's why you're asking the question, wind profile during the nighttime is obviously more as opposed to in the other part of the day, especially in some specific location. So you definitely can utilize that, and with that it's much like a pump hydro is actually kind of a very firming case, because we already have the 100%. Wind is not like that. You have only 70%, 80%, which increases the size of the battery. If you want to look at that again, that cost bracket will change if there is a wind, but wind catching area, definitely.
Okay, thank you. Thank you.
Sure.
Okay, we have time for one more question.
I have another question, but I don't, yeah, if you have one more, then you should, someone else that hasn't asked yet should go.
No, go ahead, Carol, you have the microphone.
Oh, okay. I had a question about how you pick the sizing of the battery. I know that in the test bed hardware slide, you said it was a 1 megawatt solar farm and you paired it with a 0.25 megawatt battery. And so I've been doing my own research on this, and I know the folks at NREL had said that there's no like rule of thumb, so to speak, general rule on how to pick the size. It really has to depend on the I don't know, the characteristics, I guess you could say, of the utility in question. So I just would love to hear you elaborate on how you picked that size. So
there is a rule of thumb for me, which based on my experience, which is 20 to 30% of the size for photovoltaic strengthening and supporting along with photovoltaic. If you're choosing a battery, around 20-30%, 20 to 40, I would say. Size of that PV farm will be the size in kW for the battery, with if we are using only the capacity firming, not the nighttime support, as we were just discussing, it should be a 3-hour duration. So it like a 250 kW with the 750 kWh, energy capability for a 1 megawatt PV, which is around 20%, 25%, which is little bit, low in my opinion, but 30%, 35% of the capacity of the photovoltaic is a good mix to do these functions, what I just discussed, not the nighttime support. But, holistically, when you look at it, there is no way you can look at that sizing. That's number one. Number two, people don't look at the sizing is because you don't have that sizing in your control. It is sizing and location studies are generally, there are a lot of people work on it in academics and research. We do a lot of publications too. I did myself too. But sizing and locations has got a lot of very less value in the real life because location is dependent upon where the availability is, where the people have business interests, policy associated with that, and the sizing is also related to that. So you don't have a lot of flexibility there. You use what you get, and because of your business model and whatever you call it. And so our studies were focused on irrespective of location and size. But to give you a perspective, if you are looking from scratch and if you have a capability to have size and location, that's the number. Of course, that's my number. It's not, there is no.
Okay.
Yes.
Thank you.
All right. Thank you, Sukumar, and thank you all for the seminar. This is the last in our spring series, so and I really thank the audience. Many of you have been regulars, but I do want to acknowledge one person who's been a regular quite a bit, Ralph Lambert. If you don't mind, Ralph, if you don't mind putting on the camera, I don't know if you're still around. So Ralph Lambert is a graduate of Lehigh from 1958. But he's got a very interesting history too. Grandfather Lambert was, let's see, make sure I get his name correct. Preston Albert graduated in 1883 from Lehigh. That's Ralph's grandfather. And his father is a 1929 graduate of Lehigh. And so we have Ralph, who's been attending our seminars, a 1958 graduate. First of all, I really appreciate your dedication to these seminars. And I know there's a number of you who have attended these seminars religiously, and I thank you for your attention. I just want to close by asking you if you have any suggestions on other topics that we could introduce in future seminars, fall 2022 and the spring of 2023. If you have some seminars that you think should be included in the agenda, please send me a note. Also send me a note on what are we doing right and what are we doing wrong. But I think this is a great way to end the spring session. Thank you, Sukumar, and for your presentation. I would be is it okay if we could get copies of your slides? You could sanitize it any which way.
Yeah, I can send it out, Rudy.
Okay.
Definitely.
And,
so there was one question. I don't know whether you want to have 1 minute to pick up that in the chat window. That question is, I didn't really, Edidrian, right? Edidrian, I guess. I don't, maybe not be pronouncing your first name correctly. Can you elaborate that, your question? Is on the chat?
Yeah, just to know your smoothing index, what's your target value? And
so the target value should be 0 if you have a perfect smoothing, and the highest value will be 1 if you know smoothing. And we take that at a 5-minute interval average, and we average it out to the entire 24-hour, because in every 5 minutes that slope will change. So you take that average for the entire 24 hours and then look at that number as whether we are close to 0. As much close to 0 is best.
Okay, so your range should be around 0 to 0.5 now, or is it higher?
So it can be below 0.5 is better, obviously. So right now, the one which I mentioned was 0.13 is what which I showed you in the slide. But you should get obviously all the time as close to 0. That's the goal.
Okay. Thank you.
Sorry
All
about
right.
that.
Thank you, everybody. Thanks for your attention, and see you in fall.
Thank you.
Bye-bye.
Thanks for the invite.
Thanks, Sukumar.